Is it working? Magdalene?
She's still not in Jamboard. She logged off.
She logged off. I guess, okay. Oh, so she went off of Meet, yeah. Magdalene?
She's back now.
Magdalene? Okay. I create a multi-app so that you know which apps are open on your phone. That button ya square or 3 lines or the LG fapaning so. Press it, it will all the apps that are open. At the bottom of your screen. It should be either on the left or the right of the center button. The middlemost button. I could shumisha an Android phone. Magdalene, I know your phone. Magdalene. Eh? Eh. I could remove fast one a button J3. Kia back ya arrow echo epoterilens so I get. Eh? Okay, screen. Magdalene. Magdalene. Mo screen in sa phone. Yeah.
She can also just go into the messages on this chat and there's a link to Jamboard.
Okay, try that. Yes, thanks, Nobushi. You're trying it, I get Magdalene. All right. Oh, what's that? Ubuchi Jamboard. So Jamboard is open on your phone. Kiona? So what's I bula the other time? Khanu owe buchi the other time over. Yes, smoking what trick identities. Oh, so Halloween buchi and then you are on it, ne? Okay, so we which happen no? Eh? With college. Okay, and is it showing trick identities making what delaying including sine, cos, y over r over x over r? Okay, so it's all a all right. So where I was was here to say hore, this is called a quotient identity because it is the quotient of two other trig ratios. And that quotient identity is the third trig ratio. All right, so it's just a nickname, I guess. You can think of it like a nickname, sorry. But anyway, when we solve this part, the end result is that we have y over r divided by x over r again. But now this rule tells us that we can only have y over r multiplied by r over x. And now what happens, these radii, the r's, they divide each other out to give 1. They divide each other to give 1. And then rishalaga y divide by x. And this is the trig ratio ya tan theta. Remember that. The definition ya tan theta ki y over r. So y over x, sorry, not y over r. Y over x is literally the same as sine over cos. Sorry, I'm saying tan theta is literally the same as sine over cos, or sine divided by cos. And that's known as the quotient identity. That's the first identity for trigonometry that we learn about. And then the second most important thing, theta must not equal 90. For tan of theta equals sine theta over cos theta. Can I ask you ladies, why do you think theta must not equal 90 degrees for this thing to be valid, for this identity to be valid? Why do you think it is? It has to do with the fact that at 90 degrees, one of these two trig ratios is 0, and that is going to affect how the outcome is. But I just want to get from you if you can guess or make sense of why theta should not be equal to 90 degrees for this thing to be valid. Does anyone want to take a guess? Okay, so the reason why that is so, what is the cosine of 90 degrees? It's how much?
Cosine of 90 degrees.
Yeah, it's how much?
0.
It's 0. Okay. If we have a number and we divide it by 0, what do we get as a result? We get an error, right? All right, so because theta can't equal 90 degrees, because at 90 degrees, cos theta becomes 0, and then it makes sine divided by cos become sine divided by 0, which is undefined. Therefore, at 90 degrees, we can't have tan theta. So that's the other important thing about the quotient identity. So we've done the first trigonometric identity. We can do now the second trigonometric identity, and this one is called the square identity. Okay. The square identity, let's play around with these as we see them, right? So we've got sine squared of 80 degrees. We've got cos squared of 80 degrees. When we punch that into our calculator, we're gonna do it like this, ne? So if you're working out sine squared of 80 degrees, you first work out the sine of 80, and then you square that. On your calculator, if you want to work out sine squared of any angle, right? On your calculator, you work out first the sine of that angle, and then that answer you get, you square it. So it's the same as having sine of 80 times sine of 80. or sine of 80 squared, right? So instead of writing it like this, in trig we write that square like that. So on your calculator, let's do a quick calculator exercise, ne? We're gonna work out the sine of 80 degrees. How much is it?
Sine of 80 squared.
No, just the sine of 80 degrees.
Okay.
Yeah, just say sine of 80 degrees. How much is it?
0.98.
0.98. And then square it.
0.88.
Hmm?
0.96.
Yes. Okay, cool. Now you're gonna do the same for sine, for cos. So when we
0.030.
0.030, yeah, that makes sense. So it's plus 80 cos squared. And when you add those two,
Oh, shame.
how much does it give you?
954. 0.
No. When you add sine squared 80 and cos squared 80,
Yes.
it should give you 1. Do it again. The end result should be 1. Mag-
0.8.
okay, run me through how you punch the numbers in sequence on the calculator.
Sine 80 squared.
Okay, so you don't square the 80, ne? You say sine 80 equals, and then you get an answer, and then you square the answer.
Yes.
All right.
0.96.
Sharp. And then you say plus cos 80, and then you can close the bracket and square that. It should give you 1.
0.30. What is it giving you, my D's?
How did you calculate it, Rena Magdalene? Okay. Okay. No, but like, you're using that DAL calculator, ne? Sharp.
Yeah.
Let me ask you to do this, ne? Press that bracket button, this one, that has a bracket. Press that, and then punch in the sign 80, and then close the bracket, and then press the button that squares. And then hit plus, open the bracket, then press cos 80, and then close the bracket, and then hit squared. Try it like that. I want to see what it will give.
It's done.
It gives you 1 this time.
Hmm.
Yeah. So when you square trig ratios, square them like that, right?
In brackets, yeah.
Yeah. Open a bracket, punch in the trig ratio, close the bracket, and then square it.
Okay.
Yeah. So let's do the same exercise for the next 4. But just note the one before the last has a negative sign, and it's deliberate. But I want us to see why, what difference it makes. So let's do, it's cos 23 and sine 23. So cos squared 23 degrees plus sine squared 23 degrees.
1.
It's 1, ne? And then
Yeah.
sine 50 degrees. There's no squaring in this one, ne? Plus
Yes.
cos 50 degrees. What does that equal? Let's see. Sine 50 plus cos 50. How much does it give you?
Yeah, 1.4. Yeah, same answer.
1.409, ne? Give or take. Yeah.
Yeah.
Magdalene, you also get the same. All right. Let's do the second to last one. So it's sine squared 67 degrees minus cos squared 67 degrees. Let's try that one.
0. Yeah.
It gives you 0.69, eh?
Yes.
Okay. And then
0.69, would you say 5?
yeah, because the number that, so if I'm rounding to 3 decimal places, I'll have to stop after the 4, right? But the number that comes after the 4 is larger than 5, so it converts that 4 to a 5. It rounds it up to a 5.
We are banned, guys.
I know, right?
My battery is dying.
So we're doing the last one. Cos squared 67 plus sine squared 67 should give us 1, right?
Yeah.
All right, so we're gonna prove this square identity, right? And its proof, remember we have r, we've got theta, we've got y, and we've got x, right? Y, x. Yes, so this point here is x, y, sharp. So sine squared theta plus cos squared theta from this perspective equals, sine is y over r, yes? And cos is x divided by r. So we substitute the trig ratios.
Sorry, if
Yeah.
it's possible, Magdalene, can I ask that when you're not talking, you mute so that I don't get this feedback?
Yeah. Oh yeah,
It's like a little water.
yeah, Nubusha, thanks for pointing that out. I wasn't sure which end the background noise is coming from, because I also know you have a pet, so, and I also like to leave pets to be, you know. Yeah. So, but anyway, Magdalene, just be aware, ne? When you're in the middle of class like this, that mic on, whatever sound you have in the background, we all hear it. Whose battery is that? A Bluetooth speaker. Magdalene Ongo. Yes. So the suggestion is, if you're not asking a question or responding to a question you're being asked, ne? Just be careful. Utime microphone in the call. So your microphone in the call is how you switch it off, right? In your call, you should have button a camera, le button a microphone. You just press on the turn off microphone and then it will be on mute. Then you can always switch it back on when you something. Like let's say you want to interrupt because Jambot I have a rig. Then you can put the microphone on and then speak. Then without tillage. I got sharp. So yes, so sine is different.
How come your language is so thick? You particularly, is it is coordinate?
What do you mean? Okay. I'm not understanding.
Okay, I don't think you will because you're used to it.
Yes.
I'm learning something new, Lynn Nano, so.
No, so but no, it's kind of like that when you're in KZN and our school Zulu, you know what I mean?
Yeah.
Because you literally just I had to think about it from a if I was in a workshop or a market, how would I perceive Izul masculine kumi yabona, and I know hore, when I speak it, I touch here, I touch there. Sometimes I sound like I'm still a kid. You know those things. So but yeah, but
You can't talk.
yeah, no, you'll learn. You'll learn. Don't know what. So, but anyway, just to touch on this, sine, remember it's y divided by r, and cos is x divided by r. So we simply substitute those into our equation there, ne? Which came into our identity that we're proving. So now that we've substituted, we've got y squared plus over r squared plus x squared over r squared. So I'm just gonna write the plus sign almost like it's in the middle of the fraction so that it's not confusing. At this juncture, when we have a fraction, let's say we've got 1 over 2 and we are adding it to, or rather, let me make 1 over 4. I think that would make, yeah. And we're adding it to 2 over 4, right? Which is a half. How we add them is we will say the denominators are the same, so we just add the numerators. So we can say this equals over 4, 1 plus 2, and that gives us 3 quarters. And that's how we keep it mathematically true when adding and subtracting fractions, right? And I mention this because it's relevant at this next step here. So at this next step here, we will have a common denominator of r squared. So we simply add x squared plus y squared, which are the numerator variables. But now, we also know from Pythagoras that r squared equals x squared plus y squared. And this knowledge enables us to manipulate the equation so that we can look for where there's x squared plus y squared and simply in the place of that put r squared. And this simply gives us 1. So that's why the square identity is defined as sine squared plus cos squared theta equals 1. And these identities are very, very useful. You'll see why as we get into completing these, ne? But nevertheless, I want to bring to your attention the following, right? The same square identity can be written in 4 other ways, right? And in our next class, we're going to do, or rather, let's do that for the remainder of the class. So we know that sine squared theta plus cos squared theta equals 1. If we make sine squared the subject of the formula, we will have sine squared theta equals 1 minus cos squared theta. Why is this? Because we took the additive inverse of cos squared theta and we added it on both sides, so that on this side it's sine squared plus cos squared minus cos squared, and that leaves us only with sine squared. And on the right hand side we get the 1 minus cos squared, and that gives us that. So in our book, in our learning guide on the screen, our first equation is there. Sine squared theta equals 1 minus cos squared theta. And then the second one we have is the same sine squared theta equals 1 minus cos squared theta. And it's going to get a bit trippy. It's going to get a bit weird. Now, why am I putting brackets like this? There is something called the difference of two squares when we factorize, right? If we have, I'm going to start it from where it starts. If we have a number a minus b and we multiply it by a number a plus b, the end result is, if we use distributive rule, a times a gives us a squared, then a times b, a times positive b gives us plus ab, then negative b times a give us negative ab, and negative b times b give us negative b squared. These two are additive inverses of each other, and we are left with a squared minus b squared. So now the rule is, when you have a square minus a different square, you can factorize that by saying it's a squared, it's a minus b into a plus b. You can go back and forth between these and you get the same answer over and over. Now we can apply the same thinking here. And how we're going to do that, this is also a difference of two squares, because maths today teaches us that 1 times 1 is 1. At least that's how it's been taught for the last 400 years. So we'll have 1 times 1 will still give us the 1. And then if we want to find the other factors, we'll simply have to look at cos. Because it's squared, it'll have a cos here and another cos there. But because it's difference of two squares, then we'll have different signs there. And this is, I guess, on the screen, the third one. Sine squared theta equals 1 plus cos theta times 1 minus cos theta. So that's the second way of expressing the square identity. We can then make cos the subject of the formula. And when we do that, we can also have cos squared theta equals 1 minus sine squared theta, which, if you want to solve for just cos of theta, you'll have to take the square root. So that's positive and negative 1 minus sine squared theta. And I guess you could also do that there if you want to solve for sine of theta. And lastly, cos squared theta minus 1 cos squared theta minus 1 should equal negative into 1 minus cos squared theta, and this gives us negative sine squared theta. So these four forms of the square identity are just an expression of the same thing from different perspectives. So in the one, we're looking at it from just sine. We're looking at it from sine squared if we distribute it or factor it out. We're looking at it from cos if we are working out the square root of 1 minus sine squared theta. And also, we can play around with the sign, or rather Yes, whether it's positive or negative, because I don't want to say the sign of the sign because that's confusing. It's like iron and ion. So I don't want to confuse myself like that. But anyway, if we can manipulate this very expression so that we can have even negative variations of one or more of these terms in the original identity. So yeah, and then they give some tricks here, but we'll discuss those as we do identities. Who has a question?
Yeah, kinalot belum ka jambot.
What's it doing now?
Sa jambot o lanaskan.
We're on page 3 of Jamboard.
Page 3 of Jamboard, yeah.
Actually, all of jambot nili lanaskan.
Oh, okay. It's fine. Listen, Magdalene, what I've done is called share screen. And that means you are seeing the screen on my computer on your phone. So that's why I'm sharing the learning guide. Does your phone allow you to show two apps at the same time, like multiple screens, like next to each other?
No.
It doesn't allow that. Okay. You know what, ne? Level because what I'm doing is I'm literally explaining as we go from the textbook everything, but I'm writing it on Jamboard. So I don't know. Since I'm talking and referencing something from the textbook but writing it on Jamboard, which one do you think would be best for you to follow? Jamboard. Okay. Just open the Jamboard, stick to it, and then follow there. Because the textbook is on your classroom, so you can access it anytime. But if you want to refer, we are on the grade 11 textbook. In fact, so Siavula grade 11, eh? Grade 11, we started from page 240 onwards, ne? And then the page that we're currently on now, page 250, page 250. So when you get a chance to access the grade 11 learning guide, we're on page 250 for the following example. Ne? All right, so Nobutle, remember we were doing equations not long ago for trig, ne?
Yeah.
And those ones, they had numerical values. These ones, they don't. And we have to simplify. So simplify is different from prove. It's different from evaluate. It's different from find the value of. You know what I mean? Because we have those types of equation of problems mostly in maths. It's always prove something, evaluate something. Prove is usually you have an abstract idea and you have to use knowledge that you have as a foundation to build a line of reasoning to prove that that is true. Evaluate, you are given values that you can substitute into various types of expressions and then you get an answer that's a value. I guess that's also like calculate. Evaluate, calculate, they're more or less the same. And then you get problems, Jabo, find something. So find kewo, maybe solving for an equation or using principles that are rigid to find the value of a certain thing. Like when we find a distance, a horizontal distance, given an angle and maybe a vertical height, that sort of thing. So these ones are simplify. Ne? Simplify is usually we have to use stuff that we know and find ways to creatively substitute it into what's presented to us so that we can simplify and get to the point where we cannot simplify or work this problem out further. And I'll show why with the first example, right? We're going to illustrate why. In our example on page 250, we must work out or simplify tan squared theta multiplied by cos squared theta. And tan squared theta, we know that it is a quotient, or tan theta rather, is a quotient identity defined as sine theta over cos theta. So we can simply substitute this where we see tan and have sine squared theta divided by cos squared theta multiplied by cos squared theta. I guess you can say it's divided by 1, because the fact that it's just cos theta standing alone, in fact with any number that is standing alone like this can be imagined as being divided by 1 multiplied by 1 to the power 1. But we don't necessarily have, and we can also assume that it's positive, by the way. But we don't have to write these, they're just associated with it, because the fact that it's multiplied by 1 means that it still remains as is. It still remains as is. Therefore, what we have here is a multiplicative inverse for cos squared theta, and the cos squared theta divide each other out, and we are only left with sine squared theta. So we could write this as 1 minus cos squared theta, but it still means the same thing, that we can't simplify this any further. Simplify further meaning we can't go to a point beyond where we say sine squared theta equals that, because as far as we know, sine squared theta is part of the identity, the square identity, but that's just about it. We can convert it into 1 minus cos. It's not going to do anything to solve this further. The second question is 1 over cos squared theta minus tan squared theta. And I guess we could also use the same quotient identity here. And we will have 1 over cos squared theta minus sine squared theta over cos squared theta. We've got a similar denominator, so we can just write that down, cos squared theta, and we subtract the ones at the top, 1 minus sine squared theta. But remember, if sine squared theta plus cos squared theta equals 1, that's our square identity. If we make cos squared the subject of the formula, we get 1 minus sine squared theta. And that's the same as the numerator there. So we simply have cos squared theta divided by cos squared theta, and this gives us a result of 1. So that's more or less how we simplify stuff. And you really think about it, we can't simplify 1 any further, at least from this context. Yeah, I think from our next class on Friday, we'll continue with these ones double prove. They tend to like them